All right, we're ready to get started. Well, welcome to first meeting of our revived Haskell meetup. Glad to see y'all here. We got two talks tonight. Conal will be giving the second talk, and I'm giving the first one on generic FFT, Fast Fourier Transform. So I want to thank my friend Dave Banis for inspiring me to get back to work on this project. I played with it a few years ago and put it aside, and Dave kept bugging me about it, and finally I picked it up again, and it's really quite delightful, so appreciate that. All righty, there we go. So I want to start with a little sort of fun geometrical motion idea here, which is forming paths through space by combining circular motions. So the rules are very simple. They're made up of combinations of circular motion. So each circular motion is defined by three parameters. One is the frequency, the rotational frequency. Another is the radius of the circle. And then the third one is a sort of offset, a starting angle. So there's a point on the circumference of the circle that's moving around in a given frequency, radius, and a starting angle. So that's per circular motion. And then the idea is that we're going to combine these circular motions. So each circle, we center the circle at the sort of distinguished point of motion of the previous circle. So we get these sort of nested circles in orbit of other circles. And then what we're interested in is the path that the distinguished point on the final circle takes. Okay, the one that doesn't have another circle coming off of it. All right. And then you can make all kinds of lovely pictures, kind of spirography sorts of things, for instance. And here's another example. It's sure, is that going to show up here? Interesting. Maybe I have to do something else. All right, never mind about that one. So, it did. Oh, thank you. Oh, sorry to make it go away. It was a fun example. Great. Okay. So what we have here is you can see that there's a collection of circles, and by carefully coordinating the frequencies and the radii and the offset angle, you can get them the motions to sort of collaborate or compete with each other and do quite interesting motions. And so there are a few different ways to formulate it. The first one is maybe the most familiar through some like high school geometry and trig and that kind of thing, which is we use rectangular coordinates. And so you see we have a collection of these circular motions, and we're adding them up. That's the way they combine, by addition. And here are the parameters. Each circle is defined by f, the frequency, radius, and the offset angle. And so we get this, r cos theta, r sine theta. And theta is going to depend on the frequency and the angle and time itself. All right. So that's one, but it's rather unwieldy way to express this the mathematics. A much more succinct way is to use complex numbers, and particularly in polar form. Okay, so here we have r e to the I theta. So it's the same sort of formula. R cos theta, r sine theta. You write it in polar form is r e to the I theta. So this theta is the same here. We can get more succinct still by factoring out this e to the IA. Okay, that's constant, it's not time dependent. Factoring that out. So if we pull out e to the IA, then we can combine it with r, and I'll call that x. Okay, got that? Good. Cursor is showing up. All right, so here's a simpler form. All right, and here's another example. See the kind of, what is that, 4 circles here? Each building off of the other, and we get some fun, interesting motion. So here's some questions. One is, what motions can we generate? So apparently we can do spirography sorts of things. Can we do other, maybe more organic looking things, or things with that are more more angular, say, less curvy? And then another question is, what if we want to go the other way around? So if we have the circular motions, the descriptions, we can add them up, put this formula, add them up, and we get these nice motions. What if we want to do the reverse? I have a motion in mind. Is there some set of circular motion paths that would combine to make the motion? And the answer, perhaps surprisingly, is that that you can make all periodic paths, all periodic motion paths. So if a path if a path repeats itself, so I end up going back to the starting point and it repeats itself. However, we may have to add up infinitely many of these paths, but only count limiting. And then the question of how to generate them is, well, the Fourier transform does exactly that. So the Fourier transform is what I'm going to be talking about. And what's the Fourier transform for? It's not just for making pretty pictures or pretty motions. It actually has quite a few paths. We use it roughly, not exactly, but roughly in our own physiology for hearing. Sound gets different frequency bands of sound that tickle different parts of the inner ear, the cochlea, I think they're called. Long time ago, a couple centuries before, a couple centuries BC to a few centuries after BC, we had a geocentric notion of the universe, the Earth-centered notion of the universe, and the circular motion on circular motion was kind of an important means of holding on to that belief for quite a long time, more than 1,000 years. And then all kinds of other things. So every time you do some sort of compression, not every time, but a lot of the time, do compression by breaking down a wave into its frequencies, discarding some of that information in the encoding. That's how we do compression, lossy compression. So if you mess with your treble and bass on your stereo, you're doing exactly the sort of thing. Okay. So what I showed you how to, I give a formula for generating the combined motions from the components. It turns out the formula for generating the components, and it's going the other way around, from the combined motion, right, is a very similar formula. It's kind of a beautiful thing. And then there is a discrete version. So what I showed you was a sort of temporally continuous version. There's also a temporally or spatially, works for space as well as time, discrete notion. And that is called the Discrete Fourier Transform. And if you look at this formula, you can see that there's a strong resemblance. I swapped the capital X and lowercase x because these are inverse operations. And the positive exponent became a negative exponent here on E. That's quite simple. And so the idea here is we're breaking up an interval into capital N number of pieces, equally spaced. Those are the frequencies. Those are the space of the frequencies, the different components. And we get the direct, the discrete Fourier transform. And if you look at this and you say, well, we're going to be computing capital N number of these sums, and each sum does N additions, N-1 additions. So you can see pretty easily it's going to do N squared work if it's implemented in a very direct way. And that was what people did for a while, but the quadratic nature limited the usefulness of this algorithm, as it limited the practical applicability of it. So now I'd like to, this version of the slides is not exactly the one I was hoping for, but I think it's just okay. I graduated the presentation. So first I want to show a lovely sort of implementation in Haskell of this algorithm. So again, up in the right here, this is what we're computing. I'm going to compute it in Haskell in a very simple, elegant way. It's these two definitions. So DFT, you look at this definition, just make your eyes, it's doing dot products over here, so it's doing a sum of products, and it's doing several of them. So that looks like a matrix vector multiplication. And that's exactly what this dollar with a hat on it is. It's an operation that does a matrix multiplication. So a DFT is, we got with the twiddles. Well, the twiddles are exactly these e to the negative I to I n over n. Okay. So we can form a matrix, so to speak, of these twiddle factors and then multiply that matrix by the input vector. Now, I'm using the word vector and the word matrix in a very loose sense here. It's really a much more general notion. And so hopefully you're familiar with Haskell since you're here. So what we have is the type of DFT. If you look at some structure of complex numbers, and it gives back another such structure. And well, there are going to be some constraints on F, and it's things like foldable and functor, and that might be roughly enough here. Okay. So now how do we form the matrix, so to speak, of twiddle factors, they're called? Okay, so that matrix is going to be, so it's a kind of vector of vectors, and that's the G of F here. Okay, so you can get G as the rows, F as the columns. Okay. Yeah, G is the structure containing the rows, F is each row itself. Okay, so what we're going to do is, well, each of these twiddle factors is some power of what's called a primitive root of unity. So there's going to be some e to the minus 2 pi something, and that something is 1 over n. So look at e to the minus 2 pi over capital N. All of these twiddle factors here are powers of that. Okay? So we're going to raise them to the power of k, where k goes through 1 to n, and then raise each of those to the power of n, little n. Okay? So that's what this definition here does. So inside this inside this inner call to powers, this is simply e to the minus 2 pi over n. N is the size of this data type here. Okay? So I've got a g and an f. This is the composition of two functors. And want to run into that. Just like you can compose functions, you can also compose functors. So it's, if you have two kinds of container, you can make a container of containers of values, and that's what's going on here. So the inner powers takes that prime unit of unity and forms several powers of it, and then we map over that, then we form more powers of each of them. Okay, that's how we get this matrix here. Now below the line is just some utility functions that I had defined already for other purposes. So there's something that computes the powers. Well, I wanted this to be efficient, and particularly wanted it to be parallel efficient. So I don't want to compute the powers in a sequential way. So I gave a talk probably a couple years ago now, maybe 3 years ago, on called Understanding Parallel Scan, and that's exactly what's going on here. So powers is a scan, which is just like a fold, except we keep all of the intermediate values. And a scan is a really wonderful example of an operation that seems to be, on first glance, inherently sequential, but actually has a very lovely, very efficient parallel implementation that works in log time if you have enough processing power from the parallelism. So that's what's going on here. So powers just does pure, which takes a single value and populates a whole structure with identical copies of that value. And then I do a multiplicative scan. So all of the partial products of all of the same number. And you end up getting 1, x squared, x cubed, and so on. So that's what's going on there with powers. And then this is matrix vector multiplication. And again, it's really quite general. This works for, well, these turns out to be, I think they need to be functor and foldable. That's what we need here. And so multiplying a matrix by a vector, so to speak, well, we just map. That's what this symbol is. We map over the matrix. And so for each row in the matrix, we form the dot product with the vector. That's that. And what's dot product? Quite simple. Dot product is, we do the point. So given two vectors, we do the pointwise product. So the first multiplied by the first, second by the second, so on, and get a new vector, and then sum the results. So there we need applicative foldable. That's what I've elided here. Okay. So now, so that's a very simple, direct, and quadratic time algorithm for a discrete Fourier transform. What we want is a much more efficient. So instead of doing quadratic work, we want to do n log n work, preferably with quite a lot of parallelism in there, nice fine-grained parallelism. So the Fast Fourier Transform is an algorithm that does exactly that. It computes exactly the same thing as the discrete Fourier Transform, but it does an n log n work instead of n squared work. So that's a huge improvement. It makes a world of difference in how useful the algorithm is. And in fact, it's not only faster, but it's better numerically, because the errors don't get to accumulate quite as much. Okay. And this operation has a long, rich, wonderful history. It was sort of rediscovered in the 20th century and popularized by Cooley and Tukey. So those are the names that are most commonly associated with it. But the kind of kernel insight for the algorithm was discovered earlier in the 40s, but it was really discovered much, much earlier by Gauss himself. Okay, and it wasn't published, and it was written in a funny version of Latin that was used at the time. It was quite obscure. It was a long time before people realized that Gauss himself had figured this out eons ago, centuries ago. So how do we get to this? How do we compute this? Seemingly quadratic operation in log n work. And there are a few tricks, not many. And one of them is just quite a general trick. I just wanted to sort of separate the domain-specific or the problem-specific one from this general, which is if I'm doing a summation, we're doing here, a lot of summations, and I'm summing over some number, right, so we sum from 0 to n minus 1. If n is composite, as if it's the product of two whole numbers, then you can break down that one summation into a nested summation. And all we're doing here is we're representing n, the summation index, as a combination of two summation indices. Okay, so that's what it is here. So if capital N factors into n1 and n1 times n2, then we can do two summations, one of size n1, one of size n2, and all we have to do is reconstruct the original little n in terms of those indices. So this is the same function ff. Now we're representing n by this combination. The size of one times one index plus the other index. Okay? And you can think of this as sort of a radix, like a numeric representation. If you have a kind of mixed radix, one is base n1, one is base n2, and we've got a two-digit number. So that's the mean. All right. So, so if you go and look in Wikipedia, which I did under Fast Fourier Transform, scroll down enough, we'll find the sort of general version of what's called the Cooley Tukey algorithm. And it looks like this, and it's just using exactly this summation trick. So I pulled it out to make this a little more apparent. Okay. And so this is the original summation, and all I've done is break it up into these nested summations in exactly the same way. So there's nothing clever being done here yet. Okay. And here's the cleverness, which is when we look at this, this e to the minus 2 pi I, this guy times this. If you look at this product here, and you multiply it out, so you got this sum times another sum, you multiply it out, and find out that, well, you'll have an n1 times n2 times something over here. Okay, this n1, n2 is going to divide into this. This is going to be e to the minus 2 pi times something or other. That's going to be 1. Okay, that's the point, is that this is it's an nth root of unity, so you raise it to this nth root of unity to n, the power of n, you get unity, 1. Okay, similar to yeah, okay. So this gets quite a lot of cancellation, and then do a little more refactoring, things that depend on the outer summation index and not the inner summation index, move it outside, that's this bit. Okay. So we've eliminated some of the work here. And now here's the really clever part. This is like the punchline of FFT, which is at this point, there are really two FFTs in here. So we've taken a single n1 times n2 sized FFT and reduced it to several smaller FFTs. So here's one. See, it has the right form for an FFT. And then there's this multiplication that's got to be done by the result. And now this whole thing is another level of FFTs. Okay, so I'm not expecting you to follow this. This is not really the point. Just to give you a flavor of it, you can certainly go to the Wikipedia article, and I've got links, and I'll share the slides. Okay. So this picture also came from the Wikipedia article. And it shows the basic idea of the algorithm, which is we take this one-dimensional vector, so to speak, and because its size is composite, it's the product, you can write it in a rectangular form. Okay, so that's all that's being done here. So this arrow is kind of important to follow what's going on. These are increasing indices in the original data structure. And now we're thinking of, well, if we thought of it this way, stacking it up, indices are going this way, 0, 1, 2, 3, 4, 5, and so on. Okay. Now, that equation I showed you at the end of the previous slide, it's equivalent to, well, there are two steps, as I said. One of them is going against the grain here of this data structure, so it's going vertically. It's doing FFTs vertically. Okay? Then we do that multiplication, the multiplication that was outside of that inner summation. That's what's going on here, multiply the twiddle factors, they're called in the literature. And then there's a transposition that goes on, which is just a sort of a flipping of the data structure. So instead of 3 by, 6, it becomes 6 by 3 or 7 or something like that. Okay, and then again we do FFTs against the grain. So columnar FFTs. So that's the algorithm in pictures. And then there's a question of how would we implement this in Haskell. Sure. All right, so here's the key insight in implementing this in Haskell in a generic sort of way. And by generic, I mean it applies to lots and lots of different data structure. So it was very important to me not to do an array algorithm. I'll talk about that more why. Mainly because array algorithms just don't compose nicely. All right, so the key insight is don't factor numbers, but factor types instead. So most FFT algorithms, they'll look at the size, they'll do some kind of factorization. Often it'll just be you must supply an input of size 2 to the n, and we're going to factor it by 2's. Okay? But the more general algorithm, it just needs to be some composite. So rather than thinking of it as an array and then you're doing some arithmetic, doing some factoring, we're going to think of the data type itself as already having a factored structure. And what does factoring look like? It looks like compositions of functors. Okay? So if I have, let's say, a 5 vector of 4 vectors, so that's the composition, 5 vector of 4 vectors, the size is going to be 5 times 4. So that's the thing. We get the multiplicative or the numeric factoring by doing data type factoring instead. Instead of composite numbers, we have composite functors. And we need the size in the algorithm, so that there's a simple type class sized, and sized has things like the size of the uniform pair is 2, the size of an n vector is n, and then this rule that says the size of G composed F is the size of G multiplied by the size of F. So this idea of functor composition, super powerful. It's a beautiful, powerful thing. There are like 5 basic building blocks of containers. They roughly correspond to they're a constant container, which just means there's no value of your type in it. There's identity, which has exactly 1 value of your type. Not very interesting, but that's basically 0 and 1 in the arithmetic of data types. And then we have sums of functors, it could be this guy or that guy, and we have products, this guy and that guy, and then we have compositions. It's the functor of functor, the nested functors. So that language gives us a very generic way of talking about data structures and a basis for building generic algorithms. And so that's what I used here. And composition is not only closed under size, it's closed under some of our best friends in typical programming: functor, applicative, foldable, and traversable. Meaning, for instance, if G and F are both foldable, then G compose F is foldable. And the instances are very lovely and simple. And notably missing from this list is monad. Right? Monad is not closed under composition. Compose 2 monads, maybe you get a monad, maybe you don't. Yeah. So now let's take this idea and look at our Haskell code. And so I'm going to define this FFT class. So it's a class of functors, class of container types F. And the idea is F is a container of complex numbers is going to give that container that complex number. Well, not quite. Because if you look at this picture here, there was this little transposition that happened at the end. We don't really get the same shape back. It's a bit odd. But that's what the FFT does. All right. So I have an associated type, reverse, that takes a functor to another functor. Sometimes it's the same, sometimes it's not. In this case, it isn't. Okay, so I'm calling it reverse, and you'll see why I call it reverse. All right, let's see what happens when we do composition of FFTs. And this is exactly the sort of hairy summation I showed you right here. This is what it looks like, Haskell, this one line. Okay, there are 1 or 2 other little simple definitions. So the idea here, and this is really just following the picture, what happens if we have a G of an F? Well, this un-O, did I show this somewhere? Oh yeah, so here's what composition looks like. There's a constructor O, there's a deconstructor un-O, which I elided here just for space. So here's where I'm giving a G composed F of A. First thing we want to do is, should I get this backwards? No, I couldn't have. Let's see. Oh, I might have reversed these in my typesetting. All right, first thing we do is we strip off the O. That's where I got these backwards. This really does type check. I just typeset it with some name changes. Goofed on that one. Okay, so we strip off the constructor and reveal the G of F of. Instead of G compose F, G of F of. Okay, that's what happens here. And now we do FFTs prime. And FFTs prime is this going against the grain. It's doing several FFTs. going against the grain of the structure. I'll show exactly what I mean by that. And now we twiddle. Okay, probably has something to do with this twiddles matrix. And then we transpose again. So that's exactly what happens here. We're doing several FFTs against the grain, then we twiddle, then we transpose, do several more against the grain, and then we wrap back up. Again, that O, not O, sorry about that. Okay, so what is this FFTs prime? It's very simple. We transpose, map FFTs, and transpose back. That's all it is. And that's how we go against the grain, so to speak. Transpose, flips it around, turns a G of F of A into an F of G of A. In the standard library, transpose is called, I know? Yeah, it's called sequence A. It's a terrible, ugly name for historical reasons. I like to call it transpose. That's what I'm calling it here. Okay. And now, what's twiddles? What's twiddle? I already showed you twiddles, which builds this G, is two-dimensional, a G of F of complex numbers. And now what I want to do is I have another two-dimensional thing that's this G of F of C, and I want to multiply them pointwise. Okay? How do I multiply them pointwise? Well, I just take multiplication and I lift A2, that puts it up into one level of applicative functor. Lift A2 again, takes it up to two levels of applicative functor. Okay? You have a binary operation on values, and you want to use it on structures of structures. This is how you do it. Lift A2, compose lift A2. If you got 5, you compose lift A2 5 times. So there we go. Now, there's a little optimization that can be done, and this leads to the implementation I actually use. So this is the code outside of the pulling constructor off and putting it back on. FFTs, compose, transpose, twiddle, FFTs. And then I just substitute the definition of FFTs prime here, which is this, okay? Now we look at this composition chain. We got 2 transposes in a row. Like, transpose is its own inverse. So those guys go away. And there's a standard operation for transpose composed with FMAP. It's called traverse in the traversable class. So if you aren't familiar with traversable or maybe applicative or maybe foldable, I encourage you to go play with them. I sort of resisted it for a while, had other things I was interested in, but finally I got into it, and they've become really a super important tool in my tool belt, particularly traverse, because it gives me this ability to transpose data types. So I can look at the type and I've got G of F, and I want F of G. What do? I always know the answer. Use transpose, use sequence A. Okay, so this is the code that simplify into. So I've eliminated 2 transposes, and we've fused a transpose and an FMAP. All right. So that's how we compose functions. We're going to need some basic building blocks. So we have the identity. That's not going to compose in any kind of interesting way because it is the identity. That's why it's called that. But uniform pairs is an example of a simple but still useful functor. So here's the definition. This is just an infix constructor. That's all this is, colon hash. So a uniform pair of A's is an A and an A. And then GHC can derive functor foldable traversable, as well as show, beacon, board. And so we need to know the size. Well, the size is 2. And how do we take the FFT of a pair? Well, just by taking the DFT. We can always define the FFT to be DFT because that's the specification. We want it to be faster, but it's already fast for pairs. Okay? You go through the formula, do some simplifications, sines and cosines, or the e to the I, pi over 2, I think that go away because they have very simple values, and it ends up simplifying to this. FFT of a pair is the sum and the difference. Okay, it's called a butterfly, size 2 butterfly. All right, so we have pairs and we have binary composition. I'm going to build up some interesting data structures. Well, it'll be tedious to do pair, goes pair, goes pair, and so on. So we might like to do exponentiation. Because this is a very simple notion of exponentiation of functors, which is functor f to the n. It's just f composed with itself n times. Okay? Don't confuse it with the category theory notion of exponentiation. I'm using this term exponentiation loosely here. Okay? Now, a nice thing is that if you take pair to the n, pair composed with itself, that's exactly the same as a perfect binary tree of depth n. perfect means all the leaves are at the same level. And more specifically, it's like a leaf tree, meaning the leaves are at the, the data is at the leaves. So if you have pairs of pairs of pairs of pairs of pairs, say five times, you get 2 times 2 times 2, 5 times elements, so you get 32 elements. And a nice way to visualize them is you've got a pair of, pairs of, pairs of, and so on, you get a tree. So we can do FFT on binary trees, perfect binary trees. And remember I mentioned many FFT algorithms they're often presented as you have to give input array of size 2 to the n, right? This is a dynamic condition. You got to either, the implementation's got to somehow check, or the application that's using the library has got to take a chance passing in information that isn't going to be checked. So if I make a mistake, I don't know, I could core dump or something like that. Or in a nice typeful sort of setting, we'd like this to be guaranteed correct and no runtime cost. So a nice way to enforce this size 2 to the n is to enforce it in the types, and that's what I've done here, pair to the n. It's a type that can't help, but if you have something that type checks, then it does have size 2 to the n for some n. All right. So I've suggested using functor composition, but there's a question about associativity. Okay. So multiplication is associative, addition is associative. It doesn't matter whether you add on the left, right, or on the left first, or on the right first. What about functor composition? Well, you'd hope it would be associative. Well, it does, but it does and it doesn't. The two types I'm showing here are isomorphic. They're not the same type. They're isomorphic type, which means you can interconvert between them easily. All right. So what? Are we going to get different FFT algorithms by associating differently, or are we going to get the same algorithm? Who knows? Let's find out. Okay, so what I suggest is we build right-associated. There's all kinds of ways, of course, you can associate. I want to try 2. Associate everything to the right, associate everything to the left. Functor composition. All right, well, let's see what we get out of here. If you've been to some of my previous talks, particularly on scan, you might already know the answer to this question. A related question anyway. So here's a nice simple way. There are various ways. I used to mainly do this with GADTs to do these perfect depth index trees. Here's another way to do it with type families, particularly closed type families. So this is saying RPow, so pow for power for exponentiation, and R for right associated. So given some functor h and a natural number n, well, okay, this is Haskell. This isn't really dependent type language, so I'm going to encode the type, the natural numbers in types. And we'll do that in piano's style, which is to have 0 and successor. Okay, so this says, so I'm defining a family of functors, h to the n, right associated. Okay, so what is h to the 0? It's the identity. Oh, that's nice. We have an identity functor. Let's use it there. And what's h to the 1 plus n? Okay, it's going to be h composed with h to the n. I'm going to compose on the right in this case. Okay. Now for left associated, it's going to be it's exactly the same thing, except we're going to associate on the left. So h to the n plus 1 is going to be h to the n composed with h to the 1. H. Okay. So we still don't know whether it makes any difference at all which of these two, or all of the other possible associations. But at least now we can ask the question. So here is a generated FFT. So I'm going to show you a bunch of pictures of algorithms, of parallel FFT algorithms. These pictures all came out of a compiler I developed. I gave a talk on a while back, Haskell, the hardware compiler. So here we have FFT. So you may not recognize this notation. It's a very new notation, FFT at. So this at sign is enabled by the GHC extension called type applications. And I used it before, but I didn't draw your attention to it with size. So size was a method that had no arguments, no value arguments. So how does the type checker figure out which, size for what functor? Because there's no argument or result of that type. And normally the type checker needs an argument or result to figure out, which instance of a type class you need. So when you can't or don't want to, now there's this feature in GHC Haskell called type applications, and just apply to a type. So that's what's happening here. FFT is a polymorphic function. Its first type argument is the functor, and this is the functor. So FFT applied to a right associated pair to the 0. So you can imagine the right or left with 0 of things you're composing probably isn't very important. And you're right. Right associated, left associated. There's really nothing going on here. Okay, now depth 1. Okay, so this is going to be pair to the 1. Well, really, because the way I define it, it's going to be pair composed with id, or id composed with pair. All right. So this is the right associated. That's the left associated. So, so far, nothing very interesting. So let's go to depth 2. Probably something interesting about depth 2. Go. There's depth 2, right associated. Here's left associated. So, thank you, Dave. Yeah. So Dave asked, Dave pointed out, I'm saying, this is depth 2, which you would expect to have 4, but there are 8 inputs here. Okay? I can tell you a little bit about. So these are the inputs, these are the outputs, but there are 8, not 2. And it's exactly what Dave said, because they're complex numbers, and I'm showing the values within each complex. Thank you, Dave. Okay, so 0, 1, and 2, they're about the same. So by induction, they're all the same, right? No, of course not. We're talking about associativity. Associativity is about 3 things, right? So there's really been nothing interesting to compare yet. All right, so now we get to depth 3. This is right associated, this is left associated. Okay, it really does make a difference. So these associations are all isomorphic to each other, but the algorithm is type directed, right? It's directed by the structure of the functor. So we know how pairs work, and we know how composition works. Okay, and it's not the same. It's not interchangeable. Okay, it's certainly not commutative, and even associative. It's only isomorphic. Okay, so that's size 3. Oh, sorry, 2. That's right associated, left associated. Now, there's another term I use for these trees, which is top down and bottom up. Okay, so the right associated trees are like the trees that we're used to, where a binary tree is either a leaf or it's a pair of trees. Okay? So that's probably the most familiar to functional programming. But there's another way to look at trees, which is instead of saying a non-leaf is a pair of trees, it's a tree of pairs. Okay? And that's what I call bottom-up trees. And the reason is just that for top-down trees, it's easy to get to the top structure, those pairs. For bottom-up trees, it's easiest to get to the bottom structure. Okay, because when you do an F-map, pull the thing off, you do an F-map. Okay, you either get the top or you get the bottom. All right, so these left and right trees are really top-down or bottom-up trees. And when I gave a talk a while back about parallel scan, they also led to two different algorithms that had different computational complexities. These have exactly the same computational complexity, but they have quite different structures. So here's a top-down tree, there's a bottom-up tree. Now I look at depth 4. That's the top-down, and that's the bottom-up. Okay, so interesting to me is it looks like the computation is more balanced. So think of time as progressing from left to right on the picture. Everything that's vertically aligned can happen simultaneously. So that's the parallelism in these pictures. There's no temporal dependencies. But I laid them out sort of temporally or data dependency left to right. So you could see the parallelism is how much you've got going on vertically. The sequentiality is what you've got going on horizontally. Of course, what we're looking for is lots of parallelism. But it's also nice to have balance. Okay, because if I have enough computational resources to do the kind of busy time, then I'm wasting computational resources to do the less busy time. Or I move those, I move them later. Okay, so that's depth 4. There's depth 5, again, top down, bottom up. No. But these bottom up data types, I find really fascinating for a variety of reasons. And I think they're probably very important. It's a very important programming tool, in particular for parallelism. So if you haven't played with these sort of types, I encourage you to do so. They have another name, which is regular algebraic data types and nested algebraic data type. So what a regular algebraic data type means is it's recursive, where the recursion in the type is at the same type. Okay. So in the data type, that's called regularity, regular algebraic data type. And anything you write with the kind of classic algebraic data type notation in Haskell, not the where, the GADT notation, which is a few years old, but up to that point, the only thing you could write was regular, where the recursion was at the same type. Oh, yeah? No, that isn't true. Thanks for asking. There's a different issue there, which is if you look at the kind of recursion that you need, the recursive calls in your code are going to be at a different type. And you have something called polymorphic recursion. So, ML, I think, still doesn't have polymorphic recursion. I don't know. Haskell's had it all along. And it's a very powerful tool. It's a bit obscure, but I think for parallel programming, I don't know this for a fact, but I think for parallel programming, it's a quite important tool. Okay, so here's 6. These circuits are getting quite large. And again, you can see the top-down, bottom-up seems to be a little more balanced. Now, I looked at the operation counts. So the operations are additions, subtractions, and multiplications. There are a bunch of numeric values that come from sines and cosines. Okay. They're basically roots of 2 in this case because these are binary trees. And so those operations, however, are all done at compile time. It just turns out that there are no data dependencies there because they only depend on the shape. And the shape is statically defined. Okay. Now I want to give you a contrast. Okay. So remember near the beginning of the talk, I gave a very simple, naive, but elegant, I think, definition of DFT, Discrete Fourier Transform. So Discrete Fourier Transform, remember, was the specification for which FFT is the efficient implementation. So DFT is a quadratic algorithm. So here is just depth 2, which means we just have 4 complex numbers. This is the DFT, this is the FFT. So these compute exactly the same thing, modulo numerical errors. Okay, but you can see this one is, well, it's hard to read because there's a lot going on here compared with the FFT. Now depth 3, these circuits grow, these functions grow quite large, quite quickly. Of course, they're quadratic. And here's the FFT for the same operation, depth 3. So we seem to be doing a good job here. And FFT is doing a good job here. All right. Now, I call this talk generic FFT. So what do I mean by generic? And what I mean is defining the algorithm in a kind of a type-directed way using a general vocabulary of data types as kind of a tinker-toy set. So you can, if you look at algebraic data types, you see that sometimes we've got alternation, so multiple constructors, and sometimes we have multiple arguments to the same constructor. So the multiple constructors is a sum, and the multiple arguments to the same constructor is a product. If you have just regular algebraic data types, that's all you need in addition to constant identity. If you have irregular, or what's called nested algebraic data types, you need another thing, which is composition. Okay. So if you write down your data type, I'm not saying this is true for every data type you write down, it isn't, but an awful lot of very useful data types you can look at through this lens of, this is really just convenient notation around constant functor, identity functor, sums, products, and compositions. And so if we know how to define FFT on those 5 building blocks, we know how to define it on, I'll be more clear what I mean by this. You can deduce what the operation is on your data type that you can decompose into those pieces. Well, for scans, for parallel scan, actually could come up with an algorithm for each of those 5 building blocks. For FFT, not. We know how to do it for constants and identity, some specific things like a uniform pairing, which is not part of the general vocabulary, and for composition. Okay, so this is kind of a partial success in terms of a generic algorithm. So punchline is here, if your data type is isomorphic to a combination of, identity, uniform pair, or really uniform vector, and composition, then you have FFT. In fact, you could do better than that, better or worse, depending on how you look at it. If you don't care too much about some of your data types having a very efficient, having an in-log-in work algorithm, if you don't mind doing DFT in quadratic for little pieces, little is important, of course, then you can throw those into the mix as well. Because, as I mentioned, we can always use DFT as the definition of the FFT method. Okay? Don't do it for large data types. That's the point. Do it only for small data types like uniform pairs or small vectors. Okay. Why don't we have one for products? It's really because, when I showed you that sort of key insight about taking the summation, factoring it, and then there was this little cancellation that happened with the big N1 times big N2, right? That made some of these exponentials be 1. Okay? We just don't have those identities, or we haven't found them yet for sums of numbers. Okay? So a functor composition, its size is the product of the sizes. Functor product, its size is the sum. Okay? And why is that? Well, it's really because they're tries, which are memoization structures. And tries have this kind of logarithmic nature to them. Okay, so the rules of exponents that you learned in high school apply to these tri-structures, or the relationship between tri-structures. So let's see, where was I? Oh yeah, so we just don't have them for sums, or sums or products. So this is a partial success. So that's why, you see, for instance, I don't have ragged trees, because I don't know how to factor a ragged tree into purely an exponentiation of simple data types. They don't have to be uniform like binary, binary, binary. It can be binary, ternary, quaternary, binary, and so on. It has to be a composition. All right. So if you want to do generic FFT, well, it's not always going to work. Depends on the shape of your data type. But when it does work, here's how we can do it. So this is also a fairly new feature in GHC Haskell, which is, what is this feature called? It's default types. It is default signatures. Yeah, thanks. Yeah. So for a long time, we've had, in the class definition, we give the method, right? And we can give a default. But fairly recently, but this default has to have the right type. It has to have the general type, okay? Fairly recently, there's a new feature called default signatures, okay, which can be specialized. So what this means is, if in the case that the FFT type, this type, is actually this more restrictive type, okay, and here the restriction is only adding some constraints, then here's the default, okay? So now we can define an instance where we just let FFT default, but only when these constraints hold. Okay, what are those constraints? Well, they involve something called generic. So this is also a fairly new feature. I guess it's a few years old by now. GHC generics have been a lot of different approaches to doing generic programming in Haskell. A current well-supported one is in GHC.generics. That's the name of the module. And it has a class called generic, a class called generic one. They're actually very tightly related. And the generic one is about, it's about exactly what we're trying to do here, which is take your data type of interest and map it to one of these general building blocks. Okay, and it's really one level at a time, and that is what I guess from does. I have trouble remembering which is from and which is to, because of course it depends on the point of view. So if we have a generic instance for our functor. Okay, and if the reversal, oh, I forgot, I promised I was going to explain to you why I called it reverse. It's called reverse because composition swaps its arguments, right? G of F goes to F of G. Well, F and G then also get reversed in their FFTs and so on. So all of the kind of primitives, they all get reversed. So if it's pairs, it's a bit hard to notice, except it associates the other way. Turns a top-down tree into a bottom-up tree into a top-down tree. Okay? But if you had pairs of triples of quadruples, it would reverse into quadruples of triples of pairs. Okay? Because there's a transpose inside the recursion. And so at every level, you get these functors transposed. Okay. So anyway, if f and its reversal have generics, and if the representation, that is the kind of generic representation of f, is FFTable, okay? And this bit about, and it's not like I figured this out, and the type system told me what constraints were needed here, and I put them in. Okay, if the reversal of the rep is the rep of the reversal, there now is exactly what we needed, then you can use this method. Well, what does this method do? All it does is it does a representation conversion, then does FFT, and then does a representation conversion the other way. So, and this is like very typical of these generic formulations. So this means if you don't want to write your data type as a composition, well, I don't blame you. Mostly I don't either. That's fine. Just write a generic instance that tells you how to map it one level at a time into this sort of generic representation and back out. And then, trust the compiler to make those transformations go away, remove at compile time. Sometimes it works, sometimes it doesn't. That is the optimization. Okay. Thank you. Yes, absolutely. Yeah, that's a really important part of the story. Usually, you just say deriving generic, that's all. I think in none of the examples that I use, you could do that. So, usually with a bit of grain of salt. If you use, sort of oddball data types, JDTs, this sort of thing, it's not gonna. You gotta do it yourself. I had to do it myself. All right, so I forgot to invite questions at the beginning. I'm sorry. Are there any questions anywhere in the talk? Please let me know. Motivation? Oh, yeah. I had played with the generic parallel scan. Not sure I remember my motivation for doing that. I think I was really curious about it. Oh, yeah, a long time ago, a few years ago, I read a book on CUDA, GPU programming, just horrific, just awful, awful. So it's this very low-level, industry-supported standard for doing parallel programming. But it's very low level, it's very error-prone, much easier to write programs that are incorrect than correct. If they're incorrect, they could be correct in a variety of ways, including deadlock or indeterminacy. If they have explicit synchronization. Anyway, I read this book and I was curious about how to do modern GPU programming because I'd only done old school GPU programming. And I ran into parallel scan. It's a kind of wonderful, a very, very useful parallel algorithm. It can be used to implement a variety of other operations, even sort of vision with occlusion, all kinds of stuff you can do with parallel scan. You can do sorting with parallel scan, just surprising operations. And I read algorithm, and I started with the CUDA algorithm, and I couldn't tell what on earth was going on. And so I read back to some of the references, and I found more elegant descriptions, but they still just seem like, there's some magic going on that isn't clear here. And that's what really got me interested in parallel algorithm. And I figured out, I think, the heart of how parallel scan works and expressed it in a really creative way. And in doing so, I came up with this paradigm of generic parallel algorithms, this idea of don't just do one algorithm, do an infinite family of algorithms by saying how to handle each of those 5 basic building blocks. And some of the building blocks are about composing the other ones. Right? So I'm, of course, then looking for other parallel algorithms. Interesting parallel algorithm. FFT is a very important, classic, well-known, wasn't particularly well-known to me, algorithm. And so I was curious whether, and so I started looking, and there seemed to be some hints. There's an algorithm called decimation in time, and another one called decimation in frequency, which are the two most popular, I think, FFT flavors. And they smelled familiar to me. They smelled sort of like my top-down and bottom-up scans. And so I conjectured that maybe one of them, probably DIT, is the natural FFT for top-down trees. And DIF, decimation frequency, is the natural FFT for bottom-up trees. And I really wanted to know if that was the case. That was my personal motivation. And yes, it's the case. So I was very pleased. I don't think I have a better explanation of my motivation. Have I found applications for FFT? Oh, well, I guess anything you would do DIT or do with one of these standard algorithms, of course. What I haven't explored very much is what happens when you do other kinds of compositions. So I showed you entirely right associated, entirely left associated, but every other association will come out of this and it'll be guaranteed correct. So just try anything you want, any association, it's going to be correct. And it'll have a different shape, and maybe it'll have some different useful properties, maybe not.
So if we were kind of mapping this, so the normal application is periodic.
Yeah.
So could you use something like to say, okay, I'm going to sample this, construct, and then I'm going to
Oh, okay. Yeah, so let me see if I got your question. Question is, suppose I want to do some kind of progressive, investigation of finer and finer approximations, but it's going to be dynamic. It's going to be sort of driven by, this looks like an interesting feature, zoom in, that sort of thing. In other words, get higher res. So could this sort of structure help particularly, like, not have to start all over at a finer, resolution? No idea. I think if I were to explore that question, I would want to start here because it's like a really simple, clear framework. But I don't know. So, okay. Yeah. Okay. Yeah. Okay. So this basic idea of the Cooley Tukey algorithm, which is really Gauss's algorithm, involves composite numbers. It's really about you factor a number. That's where you get started. Well, what if you have a number that doesn't factor, right? You have a prime number. What do you do? I personally don't have any experience with that, but I think what I've read is exactly what you said. You fill in some zeros to answer your question to a composite number, and not just any old composite number, but a number that has small prime factors. Now, why zero doesn't mess you up? I haven't personally looked into why it doesn't mess you up, so I can't answer that. Yeah, that's the idea. So why do you get the right thing? So why is it the case that if you do an FFT, if you pad and do an FFT and unpad, you get the same thing as the DFT of the unpadded? Why is that the case? I haven't worked it out for myself. Okay, other questions? Yes. Yeah. So F-map of a uniform pair. So that's the difference between like a Haskell pair. If you F-map, I don't know if you know this, but you can F-map over a regular old pair, and it applies the function to the second element of the pair. A few months ago, there was like a big stink when people started noticing things like this. Multifoldable, traversable, what am I forgetting? Third one, applicative, universal, I forget. Changes to the library. I personally love that. It's the only thing that makes sense if you look at the types, understand how Haskell works. It can't be anything like that, and I find it quite useful. It's a nasty surprise to some people. I think the worst surprise was finding that sum, S-U-M, of 5 tuple is equal to the last of them. But there's a darn good reason for it if you understand how Haskell works. It's really the only thing that could possibly be. So a uniform pair, when you F-map, it applies the function to both arguments. So, yes. And if you ask GHC to derive it, that's what it'll do. Okay, well, I'll just finish my concluding remarks, and then if there are other questions, I think we have time. See. All right, so what I've talked about this evening is it's a style of algorithm development I'm particularly interested in, and I'm looking for more and more examples of as I go. And it's type driven. That's what I mean by generic. It's driven by the type structure and the kind of general type structure that is the constant identity, sums, products, and compositions. And I'm particularly interested in parallel-friendly algorithms. What I mean by parallel-friendly algorithm is, well, I showed you some code. Is that code sequential or parallel? It's neither. Haskell isn't that kind of a language. It's not a sequential language. It's not a parallel language. It is a sequential language in a very different meaning of the word sequential, but not like imperative language or sequential. Okay. So what I mean by parallel-friendly is it has very few data dependencies, so it allows many computations to go on at once if you have a parallel implementation. Right. Parallel implementation can be like a multi-core kind of thing, but I'm particularly interested in massive fine-grained parallelism. So things like FPGA or GPU or who knows what will come next. And then delightfully to me, two very well-known algorithms fall out for free as special cases of this one. One is where we do all the associations to the right, the other we do all associations to the left. Okay? And of course, this suggests is that there are a bunch of other algorithms that also fall out for free that aren't well known, some that aren't known at all. And then this style works particularly well with these recent features in GHC, with this generic, with generic deriving, and with the default signatures. Allows to define defaults that work for some types, SOME types. All right. Now, as I mentioned early in the talk, it was very important to me to not do an array-based algorithm. Okay, so arrays have normally when people do parallel programming, they go to arrays right away. Okay, I didn't mean to say go to arrays, but now that I've said it, there we go. Arrays are a go-to, right? So what's wrong with arrays? I suppose some of the same things that's wrong with go-to, which is they're not structured. Right? So an array is a big blob. And yes, I can think of the array as I'm going to divide it in half and then do some kind of divide and conquer thing. But that's what trees are for, right? Trees manifest that structure internally. I don't have to, as a programmer, think in a tree way, but program in an array way. Okay? And then there's like, what about the bottom up? Okay, well, the bottom up view corresponds to taking consecutive pairs of elements, even odd elements, okay? And then consecutive pairs of pairs, bottom up. But that's a lot for me to keep in my mind. And then if I want to do things like, well, maybe it isn't a power of two, maybe it's some other composite, okay? Well, then I got to think of my array, right, as being grouped into these, kind of multiplicative little groups. But I have to manage all that myself, okay? So arrays are a kind of monolithic structure. There are the elements, and there's the whole thing. And then you're on your own if you care about anything in between. And programming is about composition. I mean, we do little bits of things, and we have great ambitions, and how do we get there? We get there by composition, by building things out of simpler things, and then things out of those things. And we want the meaning, in order to really accomplish lofty goals, it's important that the meaning at every step is simple, right? It's not like, this region of this array that has these invariants or something like that. That's all in my head. I want the sort of type structure to contain the logical structure of the algorithm. Not only contain it, but it will contain it so that then the type checker can tell me when I'm confused. So, in contrast to array algorithms, this style of algorithm is elegantly compositional. That's very important to me. Do it. Thank you. Of course not. Yeah. Thank you, Tim. All right, so let me see if I got your objections, Mr. Skeptic. So our resident skeptic points out that array accesses pick constant time, whereas tree accesses, well, you've got to kind of go follow all these pointers down the tree and so on. So we'll take that objection first. Well, it's not true. Array accesses don't take constant time. Array accesses are accesses into trees. because that's how memory chips work. All right. So memory chips, you've got a sequence of bits, and those bits are the indices into a tree structure. The sequence of bits is an index into a tree structure. All the bits, 0, I'll go this way, 1, I'll go that way. That's how the hardware works. That's how memory chips work, as I understand it. Certainly not an expert. Okay, so it's a myth that array accesses are constant time. They're not, they're log time. I've got bounded memory, I've got a 64-bit word size and so on, so you can say it's constant time. On the other hand, my tree algorithms are going to fit in there too, so you could say they're constant time. That kind of argument just makes all of the complexity, right? It makes everything constant time, so it makes the entire discussion uninteresting. So that's one response, is that in fact array access is also long time access. It literally is tree access. I think that's true. Hardware person might, you're welcome to contradict me or agree. Well, okay, so I want to say, yeah, all right. So as you're saying, in one case with trees, I got to follow multiple pointers. It's exactly the same thing in memory.
I can follow 64 bits.
You're just saying you can follow them fast. That's because logs are very small, right? The logarithm of a number is very small, so of course you can follow it fast. The same with the trees. Now, let me go on to say something else, okay? Which is if you look at the code that I generate, there's no tree access, there's no log time tree access going on. So what you see is, I really am generating an array algorithm. Right? Just look at the output and look at the input on the left and the output on the right. It's linear, right? So for compositional structure, arrays are awful. For performance on popular hardware, they're pretty decent. So what do? We don't set them against each other. That's what we do. We want the best of both. How do we get that? By programming in terms of trees and compiling, once we have the entire algorithm, into access from arrays and in arrays. And that's exactly what you see here. So I wanted to make the argument that, in fact, we're doing tree access both ways. And it's true here, too. So, in fact, I compile it to arrays, but arrays are trees inside the hardware, right? So memory is a tree. But the access, the pointers take 1 bit. And it's darned fast. And, of course, you get a whole lot of them in the clock cycle. Yeah, absolutely. And so that's what I got here, too. All right, so I linearize. I didn't talk about this at all, but my compiler, my Haskell hardware compiler, which is what generated these pictures and generates Verilog, so a little hardware description language. Yes, it also, of course, lays them out sequentially for exactly that kind of fast access. But the important thing is program in terms of trees, no arrays. Yeah, the hardware wants to do arrays fast, fine. We can give it arrays globally, but not compositionally. That's how we get high performance without breaking the composition. Okay. Okay, so let me find it first. I'm sorry, I was almost there, wasn't I? I was just a couple of slides back. Ding, 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 ding. All right, so that's what I'm talking about. How would, when I say derive generic, how would we figure out what this reverse is or something like that? Yeah, we don't. I can't derive generic here. This is so the deriving generic comes from the particular data types like bottom of trees, top down trees, and so on. For pair, we could derive generic. Let's see. Okay, so let me think about your question. Well, actually, here's a funny thing. There are actually 2 defaults. There are 2 good defaults for the FFT. One of them is via generic. Okay, and the other one is as DFT. Those are both good defaults. I don't really know which is a better default, because when I can use actual FFT, I want to. When I can't, I'll use DFT.
Well, simply answering the question, you could write, the way generics works is it gives you a bunch of types correspond to sums and products and so on, and you could write instance of FFT for the type generic gives you.
That.
And then they compose based on the instances that tell them how to compose. So you representation.
Yeah.
And then the thing that derives it takes it to this representation.
Yes, exactly.
Which then has these instances.
Thank you.
Or perhaps it's easier to think about it. If you had a type family, you could just add sort of instances of the type family for each of the generic building blocks
Yes.
and how they're put together. And then it'll work for any generic representation of type.
Yeah. And this slide that I showed you is exactly that. This compose is from GHC generic. And id is from GHC generic, and const is. So those all come from GHC generic. If I knew how to do the product functor, I'd do the one, the functor product, I'd do the one from GHC generic. And yeah, like uniform pair. That I could say deriving generic. Yeah. Yes. No, it fails because the encoding, like the GHC generic encoding for uniform pair, is a product of identity functors. And I don't know how to do FFT for product of functors. Nobody knows how. I don't think anyone knows how. Yeah. Yes. Yeah. Yeah. Exactly. Yeah. So the let's see. So the generic. Well, I think I showed you the default here. I think that your answer to your question is here, or I don't understand your question. We'll see. There we go. Okay. Let's see. There. Okay. Yeah. Yeah. So. Yeah. Yeah. So if you had a generic instance, what would it do? Yeah, I think I'll take up this question afterward. Yeah, so I don't want to burn into Decon's time. I think there is a nice answer, but there are a few pieces in motion. Yeah, the two different classes. Yeah. I'm only doing representable functors. Why is that? Well, let's see. Well, so the constant isn't representable. Can I actually do constants? I said I was, but I didn't actually do it for constants, and I just assumed it would work. But if I tried it, I'm not really sure. Okay, so Shakov is asked about representable functors. Representable functors are functors that are isomorphic to functions. Okay, so for instance, a uniform pair of A is isomorphic to functions from bool to A. Okay, this is the heart of the idea of tries, the idea of a memoization. And Shakov probably noticed that uniform pair, well, that's really isomorphic to a function. The composition of functors that are isomorphic to a function is also isomorphic to a function. So if G of A is isomorphic to K arrow A, and F is isomorphic to L arrow F of A, F of B is isomorphic to L arrow B, then G composed F is isomorphic to K cross L arrow, whatever, just that, K cross arrow. So that might be a more direct way to think about it. Yeah. Yeah, so rather than sort of structuring around functors in general, structure around classes that are specifically target these trie styles. Yeah, might be right about that. Yeah. Yes. Yeah, but then how to assemble those FFTs into a FFT of the original? That's the puzzle. Yeah. Yeah, so I don't think we can sort of, really resolve this question right here on the fly. But if our number is composite, if it's a product, our size is the product, then, well, we get to do this nice factoring into nested sums, and there's a cancellation that happens because of the product of primitive roots of unity. If there were an analogous trick for sums instead of products of sizes, for a size that's a sum of two sizes, so if you have n plus m and you do two FFTs, I think the question is, yeah, of course I can break them up and do several FFTs. Can I somehow put the FFTs back together to get an FFT of the origin? And I don't know of a way to do that. So this is a trick about summation with composite product of sizes. Let's take this offline. Yeah, either in between or after. Okay. Good to see you, Jeff. I think I don't want to go into TCON's time anymore. So, all right, I'll leave it up to you, TCON. All right, one more question. Yes. Arrays don't generalize? Oh.
One more bullet, you didn't fire.
Thank you. Okay, another point in favor of compositional types, unlike arrays, is that they're very easy to build infinite in several directions at once. Yeah. What's faster? If you have a large enough what? Branching factor?
Data set.
Oh, a data set. Oh, okay. Perhaps, yeah. Yeah, let's talk about that some more. Okay, thank you very much.